this evening's public lecture organized by the Institute for Mathematical Sciences of NUS. This evening we are very pleased to have Professor Frank Hollander from Leiden University to give the public lecture. Professor Hollander is a world leader in the field of probability theory, but he has also worked in algorithmic theory, statistical physics, as well as complex network systems. Professor Hollander has received many awards and recognition. He's a member of the Royal Dutch Academy of Science, a fellow of the American Mathematical Society, and is a very productive researcher. He has got about 150 papers written, 3 research monographs, and he is also the leader of a group that does research on networks with grants given. It's a major consortium that's funded by the Dutch Ministry of Education Culture. And so tonight, before that, I understand that he also has got 2 grand pianos in his soul, and he's a very, I believe, for a long time, a very enthusiastic pianist. But tonight he's not going to talk about his music playing. Instead, he will talk about complex network systems and how do we understand its behavior. Professor Hollander.
Thank you very much. Welcome and thank you for coming. It is certainly an honor and a pleasure to be able to give this talk as part of the Hong Beng Public Lecture Series, which is organized by the Institute for Mathematical Sciences at NUS. And what I hope to do today is to entertain you by telling you about what is so interesting about complex networks and what are some of the major challenges that we are facing in order to deal with complex networks. And here's a picture of the Institute for Mathematical Sciences, where I have been spending the past 2 weeks as part of a very interesting workshop with visitors from all over the world. And I come from a very old university. Leiden University was founded in 1575. So it's a university with very old and famous traditions. And when I come to Singapore, I'm really impressed about how fast things are going here. And also it's at Singapore University, National University of Singapore, there is a lot of work going on complex networks. So what are complex networks? Well, we are all connected to each other via various networks. So networks that we know very well are internet, through which we are able to connect through the World Wide Web, Facebook and Twitter. So I've looked up a couple of numbers. The number of people in the world who are actively using internet is 3 billion. And in Singapore, there are about 4.5 million people using actively the internet, so that's about 80% of the population. So that's a really, of course, very interesting thing. The World Wide Web, there are about 1 billion registered domain names. Singapore is not sticking out so much there. There are about 160,000 domain names, which I think is a little bit low compared to what is happening in other countries. Facebook by now has more than 1 billion active users in the world, and about 60% of the population in Singapore is actively using Facebook. Twitter has 300 million active users in the world, and about 40% of the Singapore population is using Twitter. So these are very important networks. But they're not all. There are, of course, also networks for transport. So you're thinking of trucks or trains or boats, or you have cars moving around. Mobile telephone is another very important way of communicating with each other. There are 7 billion registered mobile telephones in the world. Singapore has about 8 million of them. So 150% of the Singapore population is using mobile phones. So that's of course not possible because babies are not using them. But some people have more than one mobile telephone. It's again a major way of communicating with each other. And electricity networks are also very important. You have to transport electricity all over the place, not only to run trains and have appliances in our home and to run factories. And I'll come back to that in a second. Again, that's a very interesting network with many features of their own. And so it is definitely clear that these networks play a major role in our society today. Now, that having said that, we should also say that these networks are typically really complex for a number of reasons. They are huge in size. We've seen that already. They are typically very intricate in structure, and very often we do not even know what the structure of these networks are. I mean, it's not the case that somebody can look at a monitor and see a picture of how the internet fits together. It's too big. So we can only make snapshots of it, and we sometimes do not even know how these networks fit together. Then, on top of that, we're using these networks to do all sorts of things with, all sorts of processes. Dynamics is taking place on these networks, and that makes these networks even more complicated because of all the things that are happening with it. And very often we see that networks are quite overloaded because networks, you like to use a network to maximum capacity, and this often means that you are really pushing it to a very extreme boundary of how it can function. And if you are in peak hours, then even a network can become a little bit unpredictable, because if you are overusing it, it becomes very volatile, very prone to all sorts of fluctuations. And in fact, this could even sometimes mean that networks become vulnerable, because sometimes networks break down. There can be blackouts. There can be times when we cannot communicate with each other because the network isn't really working. So these are all issues of concern when you want to make these networks work. So this complexity, which is all put into here, is something that is of concern. And it means that we have to be able to deal with these networks in a very clever way in order to make them function properly. Now, this urgency, this major problem, was led in 2012 when there were 8 captains of industry coming together in Davos in 2012 in Switzerland, talking about how urgent these matters are. And they said, well, we are not going to solve the problem of being able to properly deal with networks by collecting even more data than we are already collecting, or by having even more powerful computers to compute things for us. That's not going to be the solution. We can do it perhaps 1.5 times better, but we need to be able to deal in a better way with the complexity of these networks. And they formulated what is called the Resilience Action Initiative. And this is a very broad initiative that says we should try to build networks that are more resilient. So resilient means more flexible, to be able to deal with varying demands, and we shouldn't make them rigid. We should allow for some extra space or slack in the system so that we can even deal with situations that are under stress. And this is a very big issue that manifests itself at various levels, even at ecological levels, and this has become known as I said, as the Resilience Action Initiative. So there's some urgency that has been recognized here. Now, mathematics is able to help. There are many areas that are involved in complex networks, and mathematics is one of them. And basically what we need to do with complex networks is we need to understand them better. We need to have good models for them. We need to find ways to control these networks. We want to optimize the networks, and many things have been happening, but it is clear that this area demands for some rather radically new ideas to really make that happen, because we are running into the boundaries of what is possible. And networks keep on growing and becoming more and more difficult. Now, why can mathematics help? Mathematics can help because mathematics is a very powerful weapon. And what is important here is, of course, the power of abstraction. What mathematics is able to do is to abstract a certain problem and think about it in more abstract terms, and then have a solution, perhaps, hopefully, for many different things at the same time. That is really the strength of mathematics, and that's where mathematics is coming in. And there are many people in the world trying to work and using mathematical ideas to indeed understand, model, control, and optimize complex networks. So what I'm going to do in this lecture, I will give you a few examples of complex networks. I will present some key questions that people are thinking about in relation to complex networks, and I will also give you a bit of an impression of what mathematics can actually offer here. And part of the line of my argument will be that it's a combination of two areas, stochastics and algorithmics, that will be that is able to make an important contribution to this area, to present a new perspective. And stochastics is basically the art of dealing with hazard. And hazard is very often a way to model complexity. Networks can be so complex and that nobody really knows what they look like, so that we say we might as well model them as something random, because we don't know anyway what the networks look like. So randomness is often a way to deal with complexity. And also, if we want to deal with large networks, we want to optimize them, we want to control them, then you need very powerful and fast algorithms to do that, to do rapid computations on a network in order to optimize them. And so also algorithmics is a major part in trying to improve our understanding of complex networks. So we believe that it's this combination of these two areas that holds promise for being able to make an important contribution. They are certainly not the only areas that are going to do it. As I said, there are many people in many disciplines thinking about the problem, but from the point of view of mathematics, we think that this is a good way to think about some of the problems. Okay, so what sort of networks do we have? I already gave you a couple of examples. Networks basically come into four large groups. So I'm giving you a classification here of networks. There are information networks. So, for instance, the Internet and the World Wide Web are examples of information networks. There are technological networks. So these could be networks of networks between banks or television, radio, and so that is another large group of networks. You have social networks. So Facebook and Twitter are examples of social networks where people communicate with each other in a social setting. And then you also have biological networks, so for instance genetic networks, neural networks. The human brain is a biological network, and they are all examples of large, complex, dynamic networks of the type that I've been talking about. These networks that we find in the real world very often and typically have two key properties which are expressed by these words which you see very often in the area. Many networks are small world. So what this means that they are very highly connected. So everything is intensely connected to everything else. And to go from one part of the network through another, you may not have to travel very far. So distances in this network are typically small compared to the size of the network. And there's a famous example which you will have heard this phrase, 6 degrees of separation. In most networks, you are at a distance of something like 6 steps away from everybody else. So if you take 2 randomly picked people on the planet, they are connected through 6 friends. So I have a friend that is connected to a friend, has a friend, and then I will be connected with somebody living in the northern part of Canada or Argentina. And this is an amazing fact, but it's really true. So there have been measurements saying that indeed, well, we are so highly connected, even though we're 7 billion people, that we are really only 6 handshakes away from each other. And this is expressed by the world, by the word small world. What is also happening in many networks is that they are scale-free. So scale-free means if you look at the network closely or a bit further away or even a bit further away, it looks essentially the same. So one could say this by saying a network has fractal properties. You see on most networks that things are not only living on one scale, they're living on many scales at the same time. You have cities, you have countries, you have continents, etc., etc. So these are 2 very common things that we simply notice are present in many real-world networks, certainly in all the networks that I've been talking about today. So let me give you 4 examples with pictures of what a network might look like. Here's a network of trucks traveling between London and the rest of Europe. And so here some of they service part of the United Kingdom crossing over to Ireland. And here there is a network where you send trucks around. And this already leads to a difficult optimization problem, because if you want to send a truck out that is going to drop merchandise along a certain route, and so you have to think carefully about how you send your trucks around to deliver. And so here's an example of a network that we know what it looks like. We know the architecture of this network because we know the roads. Here's a picture of all the airplane routes in one single day. And the light blue ones are the short flights and the purple ones are the long flights. And so here you see already a pattern of network flights by airplanes all over the world in a single day. And here again, to make this work is a highly non-trivial thing. If you want to have in Singapore, you are expecting a plane to arrive and it has obtained a slot, but if something goes wrong in New York, it means that the plane will not arrive. And maybe other planes will arrive to work. So this is a network that you can, to some extent, locally control, but you have to deal with global issues because these planes fly all over the world, and a plane can only leave when it has already an allotted slot to land somewhere. And so this is a big optimization problem. Here's a picture of all the routes used by mobile telephones in the city of Venice. And so here you see how phones are rerouted through Venice and the surrounding. And again, well, here's a network that we know what it looks like, but there are also many networks that we do not actually know exactly how. But we will see an example of that later. And as a fourth example is the network of energy. We are transporting electricity all over the country, and the difficulty with electricity is that it's very hard to store. So electricity has to be somewhere when it is needed, and it cannot arrive so much earlier. So in fact, to make an electricity network work, it's a very delicate thing. You have to know when, how much is needed at what moment, at what time, and you have to optimize the network so that the available energy is there when you need it, because you cannot store it so easily somewhere. You can, but it's very, very expensive. So these are examples that show a bit more in practice some of the questions that you are dealing with when you have complex networks. And as I have already indicated, it is a very challenging task to make these networks work properly for a number of reasons. They are large, as we've seen. There can be congestion problems because they are overloaded. And there is a fluctuating demand. Electricity is not needed at the same level at any moment of time, but it fluctuates. And one of the major difficulties is that you cannot, well, many networks we cannot control globally. If you look at a train network, in the center of the country somebody has a big screen and he knows where all the trains are running, and you have pretty much control over what is happening. But when you have a very big network of which perhaps you do not even know the architecture, how are you going to run this thing properly? The only way in which you can do this is by having local protocols that are looking at what a network is doing locally and making things happen locally and trying to optimize things, but they never see the network globally. So these protocols have to be clever so that the network, by being okay locally, is actually managing to be okay even globally. And that's a big, big challenge, especially since for many networks we do not know what they really look like. We do not know their architecture. And it is here that theory really lags behind practice. People have invented protocols and algorithms to deal with without sometimes even knowing why these algorithms work very well. They seem to do a good job, and then every now and then they don't do a good job, and we don't really understand what happened. Sometimes the reasons are very simple. There was an overdemand, but you could also have examples where things went wrong and people said, well, BlackBerry didn't work and we don't really understand what was happening. And that's where some of the challenges come, and where mathematics can help in order to abstract the problems. And how does mathematics hope to do that? Well, mathematics can hope to do that by thinking about random graphs. So a random graph is the abstraction of a large complex network, and here's a picture of a random graph that consists of many nodes that are connected by many edges, and these nodes could mean centers from which I send merchandise, or they could mean airports, or they could be electricity power plants. They could mean different things, and in mathematics it just becomes a point. And then the edges are drawn whenever there is something going on between 2 points. So an edge could mean this is a route along which an airplane flies, or it could be a street where cars can travel, or it could be a power line along which electricity is flowing. And this picture is sort of the mathematical abstraction of a complex network, so where you have nodes, you have points and lines, and of course, on these points many things can happen, and on the lines many things can happen. So, how you want to go on to model this is still gives us many possibilities, but this is sort of the key tool in mathematics with which we try to model mathematical networks. So let's have a closer look at this theory of graphs. So a graph is nothing other than a collection of points that are interconnected by lines. And the collection of points is what we denote by V, vertices, and the collection of lines by E for edges. And not all points need to be connected by an edge. Some points are not connected by an edge, others are. And by specifying which points you have and which points are connected, you get a graph. And to model complex networks, you will pick this graph G in some sort of random fashion. You will not pick a very specific graph, but you will say, I will draw it in some random way. And again, why random? That's because randomness is a way to model complexity. So you could say, I'm going to choose my G in a very random way, in some way that I can decide. There are many possibilities. And what we do is we we imagine a huge class of possible graphs, and we draw completely randomly out of a certain class a graph and say, this is what is modeling our network. And what we very often do, and I will explain to you why, is that we will think of a class of possible graphs that have a certain, what we call, degree distribution. So you will say, I will not just pick any graph, I want my graph to be such that there is a certain percentage of points that have 2 neighbors, there's a certain percentage of points that has 3 neighbors, another percentage of points that has 4 neighbors, and we choose these percentages as what is called here a power law. So the percentage of points that have exactly k connections to other points is something like k to the power minus tau, where this tau is a very important number. It's called a characteristic exponent, and it expresses typically how far points can be connected to other points. And this exponent is we just put it in as a model, and we start to play with this model to ask it all sorts of mathematical questions and say, what is this doing when I choose, when I randomly draw a graph from a very large class of graphs that have, however, a prescribed degrees. That's what we do. So this is the mathematical way of abstracting. And why are we doing this? Well, it so happens that most real networks actually have a degree distribution that is given by something like this for some power, for some characteristic exponent. Let me give you an example. Here is what is called the collaboration graph in mathematics. Mathematicians write papers with other mathematicians, and this graph, which is based on data from 2010, says how many mathematicians are there that have 1 co-author, 2 co-author, 3 co-author. So here you see that there are about 100,000 mathematicians who had 1 co-author. There are about 1,000 mathematicians who have something like maybe 15 or 16 or 17 co-authors. There are only 10 mathematicians who have a number of co-authors that is close to 100. And here at the very tip is a famous mathematician, Paul Erdős, who is a Hungarian mathematician who wrote 1,500 papers, and he wrote it with 500 co-authors. So he's the most prolific and most, collaborative mathematician that we've had. So he's an outlier here. He's all on his own, and there are a few people who have many co-authors. But this piece here, which is linear, it's plotted on a log plot. So when you move a unit here, you multiply by 2, and you multiply by 2 here also. And this line says it corresponds basically with this parameter tau being somewhere close to 2.8. So if you look at how mathematicians collaborate with other mathematicians, and a collaboration means I have an edge between me and my co-author, then that network has a kind of degree distribution that has a parameter tau. And this is a phenomenon that is not restricted to this particular case. There are, if we look at many networks, internet, Facebook, Twitter, traffic networks, it always turns out that there is a certain very widely distributed degree distribution with a parameter tau that is always somewhere between 2 and 3. Sometimes it could be 3.2, but it's that small. And it is this number here that causes this small world property. Everybody is highly connected, and etc. For instance, for this graph, there is now there's a notion called Erdős number. So the Erdős number says how many steps are you away from Paul Erdős. And many people are not so far away from Paul Erdős because they have a colleague who has a colleague who has a colleague who has written a paper with Paul Erdős. Because Paul Erdős was so prolific, he is a hub in the network, a person who is connected with so many other people that actually everybody is connected to everybody else through him. And this phenomenon is happening in many networks, also in social networks. And now you could ask yourself, but why is it that networks have this property of this highly connected, of this small world property, this scale freeness? And the reason is that these networks have this property because they have come about because they have been grown. I mean, we started with a few internet users, and now we have 3.5 billion of them. So a network grows. A network is not something that is given to you once and for all. It grows. One point that was advocated by Albert Bara, but he was certainly not the only one, is that networks grow by a rule that is called preferential attachment. If you have a new website that comes on, it probably will connect to a network, to another website that is already highly connected. Because it's so highly connected, it's very visible, and you will spot it out, and you will connect to it with a bigger probability. So when you grow a network, a new vertex will more likely connect to a vertex that has already many connections than to a vertex that doesn't have many connections. So if you go to a city, you will probably become a friend more quickly with people who already have many friends than with people who are more secluded. And so this phenomenon, this idea that a network actually is the result of a growth process with this preferential attachment property has been used to explain, and successfully, why the networks have these small world properties and these scale free. And so this is a major idea. There are all sorts of variations on the same idea that explains why networks are the way they are.
So who is Albert Bara?
Albert Bara is he's a physicist from Hungarian origin. He works in Boston, and he's been a great. He's worked on complex networks for many years, and he has been advocating this idea a lot. But it is actually a bit older.
Well, Boston, MIT, or
yeah.
and this Paul Erdős, who is he? Previously, the slide Hollander, who is he?
Hollander was a famous mathematician. He died some 10 years ago. He was a Hungarian mathematician who was traveling around the world and wrote papers with many different people. Yeah.
He's from Boston as well.
No. He was he didn't have an affiliation. He was everywhere. He was traveling around and he had no. He was basically traveling all over the world. He was a very special character. There's a nice book written about him in his life. Yeah. Okay. Now I've been talking about random graphs, saying they're consisting of nodes and lines. But once you start to do something interesting with a network, you should make your model a bit more interesting. And so we could also think of a model where you have lines of different types. Not all lines need to be the same thing. So here's a picture of a random graph where also the lines can have 3 different colors. And the color could mean a different thing. So a green line could mean it's easier to travel along this line than along a red line. So this could express capacity for sending messages or how much you have to pay to travel along this line, or how much it costs me to send electricity along this line. So you can play with different colors to make your model richer depending on what you want to do with it. And I'm going to give you 3 examples now of problems where we deal with things happening on a random graph. And with these 3 examples, I'd like to show some of the phenomena that you can describe and also what mathematics is able to do. So the first example is what happens when we want to transport something along the edges of a random graph. And you can imagine that every edge in your graph, you associate with it a certain time. That would mean how much it costs or takes to travel along this edge. And so when I draw the picture with the different colors, it would mean that green has a quick, small time to travel, red has a large time to travel, and the third color is somewhere in between. So you can associate with every edge a number, which we can also choose randomly. Again, randomness is used to model complexity. And then what you can ask yourself is, let me pick 2 points in the graph. How long does it typically take me to travel from one to the other? And here is a mathematical formula that would express this. And this, it says, pick 2 points, V1 and V2, completely at random. Then look at all possible paths going from V1 to V2. And then ask, what is the total travel time along that path? So you would sum up the travel time of all the edges that lie in this path. And then you divide by all possible choices that you could make for these 2 points, which is exactly the cardinality of the vertex set. So the size of the parameter 2, and you would get a certain number. And this number is of interest to somebody who wants to understand how effectively you can travel along a graph. So this number is it's a number that is associated with the graph, and it's something that we would call the typical minimal travel time between 2 points on the graph. And for instance, this could be the time that it takes to transmit a message from one place to another. Or it could mean how much do I have to pay to send merchandise along a certain edge when this edge is modeling a street or a highway. Or it could mean the proximity of a friendship. If you are very close to a friend, you will probably have a stronger bond with him or her and you could also express this in colors. Right? I could have a link with Louis that is really green because we know each other well, and I could have a red link with somebody that I know much less. And then the quantity that I was just mentioning would mean something like how far can you travel in a certain given time? Or if you have a certain budget to send your merchandise around the network, how far can you get with this budget? Or if you would receive information from friends, you would say how quickly does a rumor from that it originates somewhere in your friend circle, how quickly does it reach you? And this number here depends very much on the architecture of the network. So it's a quantity that is very indicative of the architecture of the network, and in particular we would like to see what this quantity is doing. So this is a degree of let's say effectiveness when I take this random graph that has this that serves as a model for typical networks, which is my random graph that I talked about before. And so let's see what you find when you do that. Well, if your network would be a regular network, just like, for instance, so we call this the d-dimensional ladder. So if d is 2, it would be a network just of basically a square grid. Then it turns out that the time that you need to travel between two different points is basically growing like the volume of the network to some power which happens to be 1 over the dimension. So this would be 1/2 in dimension 2. However, if I look at some of these networks which have hubs and high degrees, it is much less. It can be as small as the logarithm of the volume. And this is not very big. If I make the network much, much larger, the travel time doesn't really go up by much. So these networks here are highly connected. You can quickly travel from any place else to any place else. And even if I make this parameter tau smaller, if I make more hubs, if I make more points that are very deep, much connected to other points, then it becomes even smaller. And here even, it could be that even if the network gets very, very, very big, the travel time is still not growing. And so you see, so here are exactly these small world scale-free networks that show a phenomenon that says, because the networks has so many hubs, places where that are highly connected to everybody else, transport along such networks is fantastically efficient. And this is exactly the reason why internet works. If this would not be the case and internet would not have a small coefficient, we would not be able to make it work. So this is important. This is an explanation of, if you wish, it's a quantification of why complex networks are functional. Now here's another example of what you could do. We could study what happens when you put an infection on a network, and nodes that are infected can infect no other nodes to which they are connected. So nodes could travel, so an infection could travel along the network. There could be a computer virus, or you could have a population where there's a common cold happening, and the common cold spreads over the group of people. And also this you can model. Here's a famous model which we refer to as the contact process. But what it's basically saying is, if you are a node that is infected, you will become healthy at a certain rate that is independent of everybody else. Basically, you're having the flu. You say, I go home. I sit at home. I don't want to talk, see anybody, and at some point, I will become healthy. But if you're healthy, you can also be infected by neighbors. So if every neighbor of you in the network can transmit its infection to you, and you will become infected. And there's a certain rate at which this can happen, which would be a kind of contagious parameter. If lambda is large, it would mean that the disease is very contagious. And if lambda is small, it would mean that the disease is not so contagious. And you can ask yourself, well, if I put an infection in the network, am I going to have an epidemic or am I not going to have an epidemic? So an epidemic would mean most of the network gets infected, and no epidemic would mean no, it will be very localized. And if you're an epidemiologist, you will be very interested in quantifying this. And you can show that there is a certain threshold such that if this contagious parameter is below this threshold, the network will not see a serious epidemic. You will see a few people infected, but the infection will very quickly die out. But if you're above a certain threshold, you will see that the epidemic is really starting and it's infecting the entire network. So for an epidemiologist, he would like to know what this number is. And also, perhaps to say, can I do some measures so that I bring down the infection rate by vaccinating people and pushing it from the epidemic phase to the non-epidemic phase. So there's a lot of interest for complex network to quantify what this threshold is, to get your hands on this. And here is an interesting thing. If you start from everybody infected and you ask yourself, how long does it take before everybody is healthy? So how long does it take for an infected network to become completely healthy? And if you are below this threshold, then time will only grow very weakly with the size of the network. So it will take a time logarithmically in the volume of the network. But if you're above the critical threshold, it grows very fast. So if you have a network where the infection is really bad, it will take an enormous amount of time before the infection gets died out. And you really need to take measures to solve this. And if you have networks, if you're below this threshold, you don't see this. And it so happens that for the networks, the complex networks that we are modeling, this threshold is actually 0. So it means in the networks that we are dealing with that have many hubs, any infection will immediately be very bad, and it will infect the entire network. And of course we see this, if a virus enters somewhere in the network, you really have, if you don't do anything, anybody will get this virus. And it is again because of these hubs, so the few sites that there are in the network that are connected to many other people, that whenever one of their neighbors gets infected, they will get infected and they will spread the infection to many other people. So it's the hubs in the network, and we know that in most complex networks there are these hubs that will make an epidemic a very dangerous thing. And you will need to make serious measures in order to prevent this epidemic from happening. So there's a real way in which you can quantify this. The third example and last example I want to mention is what happens when you have a network and there is a terrorist who wants to somehow destroy this network. So suppose I'm having a network that percolates. Well, percolates means something like there is something like a very large part of the network is hanging together, and you can travel from one place to the other. Now, what a terrorist could do is they could say, I'm going to wipe out a number of nodes with the goal to kill the network, so that the network falls apart and is not really communicating anymore. Now, if the terrorist does this in a completely random way, he just randomly picks vertices and throws them out, he's not going to be successful in doing that. So most networks are robust against completely random attacks. But if the terrorist is clever, he could say, I'm going to kill all sites that have a degree larger than something, let's call it K star, So he says, I take 100 and I'm going around the network and I kill all the sites that have 100 or more neighbors. Then he can be very successful in killing the networks. And in fact, you can show that depending on this parameter, the threshold that he has to pick looks something like this. This is a curve that you can compute. And it says if the network has a very large value of tau, then it means the hubs are not so important, and the network is very robust against terrorist attacks. Basically would mean if you're somewhere here that you would have to wipe out almost all sites in order to really kill it. But if your network has a very small value of tau, and many real-world networks have this, tau is somewhere between 2 and 3, then actually it becomes very vulnerable, and the terrorist would only have to wipe out very few sites that have a very high degree and already manages to kill the network. And this curve is, again, a quantification of this number. So it will tell you what do I have to do to make my network really robust against certain kinds of attack. Okay. In the last 10 minutes or so, I want to tell you a few more things that lie beyond the horizon. I already mentioned that very often we do not even know what the architecture of the network is. Here's a very complicated network that looks very wild, and often we do not even know. Well, we know that the network is around, we can do some measurements on it, but we don't know what it looks like. And here are a couple of questions that you could ask yourself. For instance, if you say, if I don't know the architecture, can I do experiments to find out what the architecture is? And an interesting question is, by pushing a network to an extreme situation, does it reveal what it looks like? And this is based on some mathematical idea that comes from what is called large deviation theory. And it says, by looking at what a network is doing under very extreme conditions, you can sometimes find out how the network fits together, because every network does it a bit differently. And this is an interesting idea, which, however, has not yet been put to the test. There's no theory for this yet, so this is one of the big questions that we're trying to think about. You could also say, is a network, if a network is effective in transmitting information, can the network be made more effective by making it a little bit dynamic? So if I allow edges to change, can I make the network more effective by making the network a bit dynamic, or is it just the other way around? By making it more dynamic, it becomes more difficult. We don't know the answer to this question, and you can develop your own intuition about this, but it's a big question that we're trying to do. And again, as mathematicians do, at a certain level of abstraction. Another interesting question is, can we, by doing online measurements on a network with very fast algorithms, can we sort of see when the network is about to break down? So can we do measurements by which we say, oh, something is about to happen that is terrible to the network? And could we prevent, when we see something, perhaps prevent this from happening? A very big, very difficult question that is one of the, I would say, again, one of the holy grails of trying to understand the behavior of complex networks. And can you do very fast computations with a network that have a guaranteed level of quality? That you say, if I have to reschedule certain airplanes, can I do this very quickly and also know that the mistake that I make, that what I get is within 1% of the best solution? So these are, again, algorithmic questions, and people are thinking about this very deeply in the theory of algorithms to solve these questions. Okay, and finally, of course, what one would really like is one would like to build self-organizing networks that have local rules put into them by which they can decide on themselves how they should, change their way of operation to make them more robust and more efficient. And finally, one would even like to develop some kind of universal theory for intelligent networks. This is what mathematics would like to do. And these are big questions that many people are like to think about. For instance, here you have a car, it arrives at the traffic light, but this traffic light is not just going between red and green all in itself, it sort of measures whether there are other cars waiting and sort of decides to make this car go fast quicker. So to really build in some kind of intelligent way of regulating your traffic. These are very exciting and interesting and difficult questions, and mathematics is hard at work trying to deal with them. There are even bigger challenges ahead. If you start to study social networks, life becomes even more complicated because humans are involved, and humans are not always rational. I mean, dealing with an electricity network is one thing, but dealing with a network of humans is quite something else. And then there could be aspects of game theory involved. So there's a lot of questions about social networks in the future that will be exciting, but we will need to bring in other things, knowledge about how people behave in complex situations in order to really understand these networks. And of course, the human brain is another example. We do not know everything we would like to know about how a human brain is organized. We believe that the human brain is organized in a hierarchical fashion. And again, this is a big challenge to study neural networks and understanding what networks would do that could describe the behavior of the human brain. So big questions for the future, even more challenging than the ones that I have already mentioned. The last thing I would like to mention is that also in the Netherlands we are hard at work with these questions. There is a recent program called Networks that has partners from Amsterdam, Eindhoven and Leiden, in which we are hard at work with a whole big team of people to think about these questions. This project is coordinated by our National Science Foundation, and it is funded by our Ministry of Education, Culture and Science. Here you see a picture of us with the present Minister of Education, Culture and Science, Dr. Jet Bussemaker, who's a great person because she really knows what academic life is about and what research is about. And here we are, we just got this big consortium grant that was mentioned earlier, and we're all smiling at this happening about 1.5 years ago. And this is a big program in which there are 50 researchers involved, staff members, postdocs, PhDs. We have lots of projects running, lectures, conferences, visitors. And what we're also building is an interactive website, which we call the Network Pages, which will contain a lot of material where people can find things about networks, not only lecture notes by people, but links to literature, big questions. People can put questions there. This is a very big project that we expect to be able to finish at the end of the project, and the project is going to run for 10 years. So this is not something you do in a few months. It's not like setting up your homepage. It's a very big thing, and we're thinking about it with people from all over the world how to set this up. So I'm closing here, and I hope that I have convinced you that mathematics is able to help us better understand the behavior of complex network, and also that there are very many challenges, very many hard challenges, and there is a lot of work to be done, also in Singapore. Thank you very much.
Well, thank you, Professor Hollander, for a very interesting talk. Are there any questions, comments?
Yeah.
You just mentioned at the beginning the magic number 6. That
Yes.
you are connected to any other person in the world by 6
Yeah.
friendship and the 6
Yeah.
edges. Now, is that part of the concept of the theorem? Is the theorem saying that? Does that depend on your characteristic exponent tau?
Yeah, it depends on the characteristic exponent, and if the world would go from 7 billion to 100 billion, this number would go up to 8. So it is a number that belongs to our world.
Yes.
But the fact that when you multiply the population from 7 to 100, I hope we will never get there because our planet cannot sustain this, you would only go up from 6 to 8.
That's right.
And the 6 is to be understood in almost all of the population. I mean, there could be an Eskimo who never talks to anybody, and somebody
Yeah.
on the Falkland Islands, and they might need 8 or 9. But the vast majority of the human population
So that's
is
sort of
connected
natural.
within
Within
6.
Yeah, within 6.
Like, I mean, our distance is 1,
Why?
but within 6 you get everything. But if the network gets bigger, it will grow, but
But not-
very, very,
not so
very
much.
slow.
So
That's a fantastic phenomenon.
So it's stable.
Yeah, it's essentially stable.
Stationary.
Do they happen to know for brains, for neural network? I mean, what would they happen to have any idea or experiment? They don't know. They don't.
No, but one would expect also that there are. I would be surprised that again there you will find some exponent that ought to be really small. But of course we don't know what the network really looks like, and it's only because we are able to do these brain scans that now in the last couple of years we're able to study this, but you see some kind of not very detailed picture, and you would really have to study the whole network of neurons and the synapses and everything. And there are models for this that are reasonable, and they are again showing this phenomenon, but honestly nobody really knows. Of course, this is a big challenge. Right, you cannot measure this thing. That's why for many years, because you cannot just kill somebody, take his brain out and start to look at it. By now we have other means to do that, but we don't yet completely understand how it's organized.
Well, I mean, well, you have this issue of probing, of being able to do some probing and then
Yeah.
checks it, which of course requires you hopefully to not knock off the person.
Yeah, okay, so you can ask, so for instance, there's clearly a hierarchical structure. So there are things like, you can ask me, like, Frank, how was it yesterday? And I could say, yesterday? Well, you went to this piano concert. Ah, yes, of course I went to this piano concert. I need 10 seconds to remember this. And then you could also ask me, what was this girl's name sitting next to you in kindergarten? And I said, Marieke, and I will know it immediately. And I haven't thought about Marieke for 50 years. Now, why is it that I remember Marieke after 50 years? And I remember her instantly. And I had a lot of trouble remembering what I did last night. So this is amazing. And so this must mean that there is Marieke is stored in my brain in a way that I don't understand. And I haven't thought about her for 50 years. So it's amazing. But it will be, again, small world, scale-free, definitely. But maybe in some more fancy way than we can even imagine.
Any more questions?
So I want to ask you, on the previous slide, you say the ultimate goal, the third one, there's a group of people there. What are they doing?
Sorry, to watch.
The ultimate goal slide. The first one you said it traces to make the car move faster and quicker. Can you come back to the
This slide?
No, the ultimate goal. The ultimate goal, the car move faster and quicker, and the center is the wing energy.
Are you talking about This
this
picture
one,
here?
this one. Yeah,
this picture here.
Yeah.
Yeah.
No, I say about this group, the third group.
Yeah. Okay. So here's another example. So here you have, for instance, if you want to, you may want to couple various different networks, right? Because you want energy available. Maybe you can put sun power together where you say, well, when there's sun, I can use the sun power. If there's wind, I can use this. Now, this group is sort of saying, well, here, this is really a joke. It's a bunch of people sitting in the desert, and they're trying to have an internet connection, trying to connect up with the rest of the world, and you would like to make every part of the planet available, even the remote spots where they're looking at. So it's a bit of a pun.
One
Yes.
thing you mentioned networks where you're dealing with rational people, but of course there's a network that we know very well, economics.
Yeah.
So have people applied this, what you're talking about, to economics?
Yes, indeed. I'm working in Leiden with a colleague called Diego Garlaskendi. He's an econophysics, and he did something very interesting. He looked at the structure of the network of banks over time, both before and after the crisis. And he found that this changes, and it changes well before the crisis. He noticed that already 3 years before the crisis, the network through which banks were trading sort of changed in the sense that they didn't watch each other anymore, they were more concerned with themselves. And he was able to quantify this, and then it took 3 years later that you really see that the whole system fell down. So he says there was a period of 3 years where something already was in the air. Now he said, if I would have known this, it doesn't mean that you can prevent a crisis. But a crisis announces itself, and he has clear evidence from saying that the strength at which banks were trading was already changing well before the crisis. And people, again, started to just be worried about themselves, and it's difficult to get these data because banks are not telling you what they're doing. And so, yes, indeed, and he's been using networks model to deal with this. And then, of course, you can ask, well, why isn't it happening? That's a big question. Probably people lose trust, and so there's something about trust. It's a much more complicated network than a big electricity grid. So yes, there is a lot of interesting things going on there as well. Yes?
I was thinking about this electricity grid. For a lot of these networks, we have this rule of 6 degrees of separation.
Yeah.
But on the electricity grid, physical shape of the Earth, you can't connect China to
Exactly.
Spain. So is this network really different? That it doesn't have this property?
Yes, this network would be different on a very global scale. I mean, you will not put a power line between China and Argentina. But they are so there you could say locally there's a certain structure, and on a bigger scale the structure is of course changing. So for electricity networks, the network has certain properties up to a certain scale, probably just the scale of a large region. So indeed they have to be treated in their own way, and this is very often, depending on what you want to do with the network, you will make certain assumptions, and not everything fits the same rule. But there is a certain commonality also in these networks. You like to make them very connected so that you can send your energy very quickly to where you want, because it's really delicate. If you send too much, it's lost. And this can amount to a lot of money that you lose, or people have to find that they cannot switch on their refrigerator anymore to certain hours of the day. Yes?
One of the things you were talking about, it certainly sounded like you were imposing a metric, some sort of a metric on the network, but what mathematicians would call
Yeah.
and perhaps Is that something that people, anyway?
Yeah, for instance, if you could say how many edges do I have to travel? That's a metric. But what I was doing is I was assigning travel times to network. So and I chose them randomly because of complexity reasons. And then of course you essentially have a random metric of the network. And there are various different choices you can do, and depending on the choice that you make, you will find certain properties. But there is somehow a red thread running through everything, that a certain number of things that you see on appearing in different forms. The big challenge for mathematics is not only to explain this, but also to quantify it. To say, well, how efficient is something really? Because that's like the example I was talking about, the epidemic. So, well, you would like to know how hard it is to suppress an epidemic. And maybe you have to have severe measures. Maybe your conclusion is everybody has to be vaccinated. Maybe you say 10% of vaccination is enough. 20% is enough. Well, you better know what you are out there to do. And that requires a quantification, and then you will get into more detailed questions like what is exactly happening.
Can you say something more about the large deviations and the nature of the network? How does it?
Yeah. So here's a technical remark. Every random variable has its own unique rate function. If you use Kammer's theorem, so this is a technical thing, large deviation. So somehow, if you ask a system to do something highly unusual, it will do it in a very specific way that is somehow best tuned to what the system itself is. You say to the system, you have to do something very difficult, and then it says, I'm going to do it in the least difficult of all the difficult ways. So I'm optimizing something. And this optimization problem very often is unique for the system itself. Not always, so that you can somehow, by seeing what a system does when it is put under big stress, that you could say, aha, you must look like this because you are the only network that would do it in this way, and another network would have done it in another way. It's a big dream. And so one of the things I'm trying to think about is that, but it's very hard to quantify, but I do believe there is something there. And the deep root for this is that Kammer's theorem, every distribution has a rate function, every rate function is a distribution. And it's a one-to-one relationship. So that's somehow...
It should be that every network has some sort of proper statistics, so to
Yeah,
speak.
exactly. And hopefully you can learn a lot
and
from
you
the
know
network.
how the T's look like.
Exactly.
How do you characterize self-organizing networks?
The self-organizing means here that you will have local rules. The network is so big that there's nobody looking at the network and saying, I'm behind the steering wheel, I decide what has to be done. You have to tell the network locally to make its rule. And that's what I call self-organizing. You put local rules. You say, well, if there is here a peak in the electricity, please stop producing here, even though maybe I don't know the entire network. And that's what I would mean self-organizing. The network is organizing itself using local rules, and there is nobody steering the network from the top, because two large networks, that cannot be done. Of course, if you have a train network, there are people looking at the screen, and they are not self-organizing networks. But probably the human brain is a self-organizing network. And well, you can say, well, we are organizing it, but you're doing something in your memory which is amazing. And this is not a global thing, this is probably a local thing.
The brain is so quantum.
Yes, yeah, maybe we have a quantum brain. And which means that we need quantum algorithms and a quantum computer to solve our quantum brain. Wonderful challenge. Well, if there are no more questions,
One more question. Can you
Yeah.
go back to the high-speed rail? It's a two-way or one-way?
yeah.
This one is a two-way or one-way?
No, this is again a picture. I have a couple of pictures where I just wanted to say, if a network has this scale-free property, which is this whole group, you see that the time to travel is very quick. So it means the network is very efficient, and I use this little picture to say of a high-speed train going from one to the other. So don't take this literally.
So it's a
Tau
black G is approximate, right?
Yeah, tau G is approximately the time that it takes me to travel from between two arbitrarily picked points in the network. And it's very high in organized networks, and it's very low in these networks that are scale-free and small worlds, which for this particular group of networks that I introduced is quantified here. So these are very small numbers, and you see that even if it's log, I can make the population go from 7 billion to 100, I wouldn't even notice it.
To 100 million.
Yeah, no, 100 billion. If
Oh, sorry. So it's 7 billion to
7 billion people on the planet now. But I claim if they would become 100 billion, we would still be easily communicating with each other via internet. No difference whatsoever. So the network, the internet is a very, very robust network for communication.
So please join me in thanking Professor Hollander for a very interesting and I'd like to take this opportunity to present to Professor Hollander a token of appreciation on behalf of the IMS. So this consists of two things inside. One is the IMS name card holder, and the other one is an IMS coffee mug.
Okay.
With the inscription of the Navier-Stokes equation.
Okay, wonderful. Thank you very much.
Plenty of coffee and
yes, I will put it on my desk and look at it every day.
Thank you very much.